this video, we're going to talk about gas stoichiometry. All right, so basically gas stoichiometry is just stoichiometry, but with gas laws, either on the front end or on the back end, or maybe on each end, depending on exactly how they set the problem up in the first place. All right, so therefore the steps are essentially the same as any other stoichiometry problem. You've got to convert to moles. You've got to use your mole ratio, and then you do whatever else they're asking you to do, which is going to depend on the details of the problem. Okay, a couple of frequent shortcuts, though, that are going to get mixed into these. I'm going to address these as they come up. The first step, or the first shortcut that you can frequently make is that 1 mole of gas is 22.4 liters at STP, which, remember, STP is 0 degrees Celsius and 1 atmosphere of pressure. If it's not at STP, don't use this shortcut. It will not be valid. All right, find your notes packet. We're going to look at all 3 of the gas stoichiometry examples in turn. Example 4 is already written out up here on the board. In this particular case, I didn't give you a chemical equation in the problem. So sometimes I'll give you an equation, sometimes I'll not. Sometimes the equation will be balanced and sometimes it won't be. In this particular case, you don't have any kind of an equation at all, but it does describe the reaction. Okay, so if you like, you can pause the video, take a moment to write out your own chemical equation for it. I think that would be good practice because it's been a minute since you maybe had to do this last in class. So pause me, write out the chemical reaction, and try and balance it as best you see fit. All right, carrying on. It says magnesium reacts with hydrochloric acid and produces magnesium chloride and hydrogen gas. All right, magnesium on the periodic table takes a 2+ charge. Chloride is 1-. Therefore, magnesium chloride is MgCl2. And of course, hydrogen gas is diatomic, so that's H2. So a correctly balanced equation then would just require there to be a 2 placed in front of the HCl. Okay, so then the question wants to know at STP what volume of gas is produced when 5.25 grams of hydrochloric acid reacts. Okay, so first step is convert to moles. We know we've got 5.25 grams of hydrochloric acid that have reacted. Okay, molar mass of hydrochloric acid is 36.46 approximately. All right, so let's see. That would be my first step, is I'd have to convert that to moles. I have done that. Step 2, mole ratio. The mole ratio of hydrochloric acid to hydrogen gas, which is the thing that they are asking about. The only gas produced in this reaction is the hydrogen gas. This would be aqueous or solid or something along those lines. The mole ratio of hydrochloric acid to hydrogen is 2:1. Based on the moles of HCl being up here, I need 2 mole HCl to be down there for every 1 mole of H2 that's produced. All right, third step is whatever else they want you to do. In this particular question, they wanted to know the volume of gas that's produced at STP. Our first shortcut here was that 1 mole is 22.4 liters at STP. Well, they said at STP, so therefore we can use that 22.4 liters per mole as a shortcut. All right, so that's my work all in one line. And the calculator says, apparently 1.61 liters, assuming I didn't make any typos. And that should be the correct number of sig figs, because remember, these are considered infinitely precise, and this is also considered infinitely precise. All right, so really this is the smallest number of sig figs in the calculation, therefore 1.61 liters should be our correct answer. Example 5 is a different reaction. This is the synthesis of ammonia reaction. And this one is intended to demonstrate the second of my frequent shortcuts that I mentioned you could take. The idea here is, since moles of gas are proportional to volume. Instead of a mole ratio, you can just use a liter ratio. Okay, what am I saying there? Well, okay, the mole ratio of, say, nitrogen to hydrogen is 1 to 3. Okay, fine. 1 mole of gas at STP is 22.4 liters. So that means that there is a specific relationship between moles and volume. Therefore, if 1 mole of this reacts with 3 moles of this, it's also going to be true that 1 liter of this reacts with 3 liters of this because moles and volume are directly proportional. So that actually allows me to cut out several steps, right? I don't actually, in this particular case, have to convert 10 liters to moles, right? I don't have to do step 1 and then do a mole ratio and then convert back to liters, since that's what they're asking for, is how many liters of hydrogen must react. I don't actually have to do all of that. Instead, I can condense all of those 3 steps down to simply a liter ratio instead of a mole ratio, since 1 liter would react with 3 liters. 1 liter of nitrogen would react with 3 liters of hydrogen. Okay, so here's the work using the shortcut. We got 10 liters of nitrogen. As stated, 1 liter of nitrogen would react with 3 liters of hydrogen, giving me the result of 30.0 liters of hydrogen are required in order to react with 10 liters of nitrogen. All right, now if I insisted on, no, I've got to do all 3 steps, okay, here's what that would look like. 10 liters of nitrogen. Well, if I think that I have to convert that to moles, they do tell me it's at STP, so 22.4 liters of nitrogen represents 1 mole of nitrogen. Great, I have converted to moles. Step 2 is the mole ratio, right? 1 mole of nitrogen reacts with 3 moles of hydrogen, all right? And then the last step, again, if I thought I had to do all of this, is I'd have to convert from moles to liters, because they wanted to know the liters of hydrogen. And we're at STP, so 1 mole of hydrogen is 22.4 liters. Okay, notice in my math here, I am first dividing by 22.4, and then later multiplying by 22.4. Those 2 steps are going to exactly undo each other, meaning I didn't really have to do all of that, right? That was not necessary because I was talking about liters of gas in both cases, right? So as long as you're only talking about liters of one gas reacting with liters of another gas at the same temperature and pressure, you can simply say that the mole ratio is in fact a liter ratio. All right, so long and the short of it, this is in fact all of the work that I have to do for example 5. This is not wrong, but excessive and unnecessary work that just ends up undoing itself. Okay, example 6 is about the reaction of aluminum with chlorine to produce aluminum chloride. First thing I'm going to do is balance the equation because I know I'm going to have to do that anyway. 2, 3, 2 are my balance coefficients. All right, now reading the question, they're telling me a volume of chlorine gas is reacting with an excess of aluminum. All right, so that means I don't have to worry about how much aluminum there is. This is not a limiting reactant problem. Okay, and then what mass of aluminum chloride will form. So they're telling me about this, and they want to know about this. All right, first step in any stoichiometry problem is convert to moles, if you have to. Well, we have to. They told us that we've got 5 liters of chlorine. That's not a number of moles. And they're asking about a mass of some other substance, which is not a gas, right? So we won't be able to take actually either of these 2 shortcuts. Oh, Mr. Erica, why can't I do the first shortcut? Because I could just say that, 22.4 liters is a mole and converts it. Nope, that will not actually work in this case. This is not standard temperature and pressure. It doesn't say STP. It doesn't say 1 atmosphere and 0 degrees Celsius. This is not STP. I can't just divide by 22.4. So my first step, in fact, in getting moles of gas, or moles of chlorine that react, is PV equals nRT. There's not really another way to do it. The pressure is 785. Oh no, don't plug that in. That's millimeters of mercury, and you should remember it needs to be in units of atmospheres. So divide by 760 to convert to atmospheres. Okay, volume was given. That was 5.00. Moles is what we were looking for. R is the usual 0.08206. And the temperature is 25. Oh, Celsius. I hope they didn't get you with that. Celsius needs to be converted to Kelvin. And the calculator says the number of moles is 0.211 moles of chlorine. Okay, great. Next, we were supposed to find the mass of aluminum chloride that will form. So I've done only step 1 so far. Now it's time for the mole ratio. Mole ratio of chlorine to aluminum chloride is 3 to 2. You can pause the video, by the way, if you want to just churn through the stoichiometry and see if you know what you're doing. I think that's honestly a good idea. Pause, resume when you think you got it. Okay, mole ratio is 3 to 2. That 3 should go on the bottom because I have moles of chlorine up here, so I need moles of chlorine down there. 2 moles of aluminum chloride goes on the top. They are asking for the mass of aluminum chloride, so therefore I need to do the next step, which is multiply by the molar mass, which is 133.33. Wow. All right, and the calculator says the answer is apparently 18.8 grams of aluminum chloride. Again, unless I messed up my sig figs or have a wrong value or something. That is, I think, everything with example 6. Now, there is the possibility, remember, of a limiting reactant problem. So suppose, hypothetically, they had said something like, instead of with an excess of aluminum, they had said with 5.00 grams of aluminum. All right, now, had they done something like that, there would be additional steps. So 18.8 grams of aluminum chloride, then, would be the amount of aluminum chloride that we would get if chlorine is the limiting reactant. All right, we don't actually know that the chlorine is the limiting reactant, right? So we did all this work, we found out how much aluminum chloride would be produced, but that's all assuming that all 5 liters of the chlorine reacts. It's possible that we have an excess of chlorine and all of the aluminum is in fact going to run out first. So if they had given us information along these lines, we've got 5 liters of chlorine and 5 grams of aluminum, one of them has to run out first and we don't know which. Okay, so that means that we are going to have to do now a second calculation to determine which of those 2 is in fact the limiting reactant. All right, now, based on the work that I've already done right here, the work that I'm going to choose to do is this. I'm going to say, what if all 5 grams of the aluminum reacts? How much aluminum chloride would this produce? Okay, all right, so let's run through that. 5 grams of aluminum. Convert to moles. 26.98 grams of aluminum per 1 mole of aluminum. Mole ratio, 2 to 2. All right, that really won't change the numbers, but I'm going to put it in here because, like, look, man, I'm teaching chemistry here, right? I got to do it the right way. All right, and then in this case, in order for me to be able to compare the results, I'm going to get the grams of aluminum chloride that form. Okay, so molar mass of aluminum chloride, 133.33. All right, after typing all that into my calculator tells me that this would produce 24.7 grams of aluminum chloride. All right, now if you think way back to when we did limiting reactants, right, the thing that we said to do is always choose the smaller result, right? The smaller result will correspond to the one that actually runs out first. Okay, so if all of the aluminum reacted, I could get 24.7 grams of aluminum chloride. But all of the chlorine reacting will only give me 18.8 grams of aluminum chloride. That's a smaller result. That right there is telling me that the chlorine is the limiting reactant, and therefore I choose this as the answer. So in fact, given this modification to the question, we would get still 18.8 grams of aluminum chloride. Okay, good. We will answer any other questions that you might have in class, so good luck with the homework, guys.